Here's a picture of pressure transducer captors in a spark plug hole while the engine's running. Lots of information here if you can decipher it, which I can't. Too many humps, too many bumps. Got these big ones over here and these little ones in here and all this funny stuff on the bottom here. Not real sure what it all means and don't really care. Really, this doesn't have a whole lot to do with what we're going to talk about, but I thought it was pretty, so I'd put it up here just to start things off. Mr. CRB started this little episode when he put up a capture of a Hummer that apparently had some plugged exhaust, and it led to a whole bunch of questions. Let's see if we can do a little bit of research and we'll answer those questions. This is a capture I made the other day. I put a socket and a big bar on the front of a car with a transducer in one of the cylinders, and this is what I got when I cranked the engine over a half a turn as fast as my feeble little arms could do it. As you can see, I got 80 pounds compression out of this thing, turning it by hand, and when it hit the bottom, there's about 16 inches, 17 inches of vacuum. And then I got tired, so I had to quit. But I did try it again, and I was still tired. As you can see here, I didn't quite make it all the way to the top, and I did get the same kind of reading though. 87 pounds compression the second time I tried it, and 16 inches of vacuum about. And this is just cranking it over with a bar, a breaker bar in the front, about 2 feet long, on the front of the crankshaft. So originally I thought the faster you crank it, the more compression you should get, right? You're squishing the contents of the combustion chamber, and instead of calling it that, let's just call it the stuff. Whatever's in there, whether it's fuel, whether it's exhaust from the EGR valve, whether it's just air, whatever it is, we're going to just call it stuff. So when I get stuff in the combustion chamber and I push the piston up slow, I'm going to get compression. There'll be a little bit of leakage past the rings, possibly past a cylinder that's not really round, past valves leaking a little bit, because it's not really 100% airtight. So some of the stuff is going to sneak past the rings, and it's going to go out, so that the compression will be affected. So as fast as I could turn it, I got the stuff to squish down quick enough to make 88 pounds here. So at, let's say, 4 or 5 RPM, turning it by hand, I get 80 pounds. If I can use a starter to turn it over, I'm thinking I can get a whole lot more pounds out of it, because it's going to be turning a whole lot faster. So I kicked the starter in, and I got a little bit more pressure, but not a whole lot. 123 pounds here, pressure. First crank is a little bit higher, and then they get a little bit lower. Kind of interesting. Why do you suppose that is? See if we can find out. So by the look of this, it looks like if I kept cranking it, because of this line, that the compression would be getting less and less and less, and that don't make sense. So I cranked it a little bit more, and it's not true. It finds its level, and the compression remains exactly the same all the time. So what's going on with that other capture? This is back where we were. So the very first engine revolution you see is the highest, and it doesn't have one of these small negative pressure areas before this one. It's interesting. Right here is not here, and it has higher compression. Let's remember that. So this is actually cranking for an extended period of time. 109 pounds about compression. Let's take a closer look here a little bit. And it's got like 12 inches about of vacuum at the bottom of the compression stroke. And you can see where the intake valve is open. Depends on where you want to put this. If we use the bottom, it's got, you know, 5, 6, something like that inches of vacuum during the intake stroke. And there was what I thought was a myth that when you do a compression check, you always hold your foot to the floor to keep the throttle open, or the carburetor is actually when the theory came about, to get the true reading. So I thought, well, this is a pretty good time maybe to check that out. So I did the test again, and I put my foot to the floor and cranked it over, and when you know it, compression is substantially higher, 12 pounds or so higher. And the vacuum dip is lower after the compression stroke, and there's no vacuum whatsoever right in this area here. Right where the intake section is, zero vacuum, obviously because the throttle is wide open. So I'm gonna make a bold statement that when you eliminate the vacuum or the negative pressure from the intake stroke, it causes the compression to be higher. Because if you're starting your compression stroke with negative pressure in the cylinder, the piston might have to go halfway up or a quarter of the way up before it gets back to atmospheric pressure, before it can start to squish the stuff. So that's why if we would go back to the starter one, the very first crank had higher pressure because there was no negative pressure in the cylinder before the starter started turning it. So it was harder to squish all the stuff because it had a full cylinder of air stuff in it. But after it had turned over once and it had an intake stroke right here that actually created more of a negative pressure, the negative pressure counteracts the compression stroke and actually brings the compression down because there's less stuff to squish. Probably I didn't word that very well, but for an old guy with a lisp and a wooden leg, that's the best I could do. So here's the starter one again. So first one is high, and then it goes down until it reaches the level, the pressure in the intake gets stabilized, and then it remains the same. Unless you put your foot to the floor, then the pressure goes up slightly. It's because, oops, this is not that one. Oh yeah, this is pedal to the floor. I got confused. This is the pedal to the floor because there's no negative pressure right here during the intake part. So now that we got that straightened out, if you raise the pressure in the intake, the compression will go up. Just because of the amount of stuff in the combustion chamber to get squished. So if my theory is correct, or as it was correct, the faster you crank it, the higher the compression, then why, when it's idling, is the compression way lower? And we know it is because we all check it and we know that it is lower. And you don't have to believe me because I did it. So here's the engine idling. And I didn't have any filters on or anything, so it's a little bit scabby looking. And the compression idling is only 64 pounds. Now, without a spark plug, idling to me is just turning over really fast compared to with the starter. Starter at 200 RPMs, idling 800 RPMs. I would think we're not changing anything other than we're turning over faster, but what we are changing is the negative pressure in the intake right here, right in this section. Now with this one, we have 20 inches of vacuum. So the piston has to go a lot further up to get rid of the negative pressure before it can start to squish the stuff. And that's why the pressure in the cylinder is so much lower idling, because there's so much negative pressure right at the beginning of the compression stroke. Right here. This is where the intake valve goes closed. Right here where this little mark is here, right by that cursor, the intake valve goes closed right there. So the piston has to bring this negative pressure back up all the way to here, to 0. So if this is the top, and make this a cursor, and the piston has to come to here, right up here, that it has to come almost halfway up to the top of its stroke before it gets the pressure back to 0. So it only has half a stroke to make compression, because right here is 0. So when the piston gets to this spot right here, it's hard to keep an arrow when it keeps running over those lines, but right where the compression stroke crosses this dotted line here is 0. The piston's halfway up by this time. So if you have a 4-inch stroke, you only have 2 inches left to actually make the compression, and that's not a lot of space to squish all that stuff. Okay, that's enough of that. Everybody thinks I'm crazy by now anyway. So now let's address the question or the statement. Seeing as how there was no punctuation after it, I don't know if it was a question or a statement, but restricted exhaust causes higher compression. So this car was idling right here, just like this. And I went around the back of the car. This is a 4-cylinder engine. And I plugged the exhaust. Now, I'm not real strong, so I couldn't plug it right off. And this little 4-cylinder fart would have coughed and died anyway. But I did this. So I plugged the exhaust while it was idling. And I plugged it on screen 3. This is screen 3. And just in case Rich doesn't believe me, here it's idling, right here. It's got 58 pounds compression about idling. We'll call her 59. There it's idling. Wants to see the whole thing maybe. Okay, idling along here. Screen 3, I plugged it, and the compression goes up considerably, I might add. 30 pounds higher by plugging the exhaust. That's quite a bit. And I got somewhere around 10 pounds pressure in the exhaust system. And I raised the compression 30 pounds. That's fairly significant, I think. And I didn't make it up. It's for real. You got to believe me, Rich. I'm telling you the truth. So why did the compression go up when I plugged the exhaust? This is the plugged part. This is screen 3. The exhaust is plugged at this part. 10 pounds about. And what was the intake? We'll call it 15 inches. The vacuum in the intake. When the exhaust is not plugged, 20 inches of vacuum. So plugging the exhaust obviously makes the engine labor and makes the pressure in the intake go up a bit, which in turn drives up the compression. There's right there, you can see the less vacuum in the intake manifold when the valve is open creates the compression in the cylinder to go slightly higher. 30 pounds higher in this case, as we've seen. One of the other statements or questions, whatever it would be, is that higher RPM makes higher cylinder pressure. Well, let's see. Had the car idling right here. Pressure's low. Put the whole thing on. And I revved it up. I revved it up to 1800 RPM. And I held it there. And what do you think happened? Cylinder pressure actually went down. Didn't go up, it went down. It went down 12 pounds. Why do you think that happened? The vacuum, when it was high, is about 23 inches of vacuum. See the vacuum here? When it was idling, probably 20 inches or 21 inches. So once it got happy with running that fast, and the vacuum in the intake system stabilized at a bigger number, less pressure, more vacuum, whichever way you want to do it. It affected how far the piston had to travel in the combustion chamber and actually brought the compression down. That was my finding anyway. But what about if we left it in gear? So I did it. Pretty tough on this old Dodge, I'll tell you. Here it is idling again. Same thing. Idling along. And then I revved it up. And I went to the same RPM, 1800 RPM in gear. And I held it there. And look how much higher that compression doubled. It was at 59, 60 pounds before. And look how high it went when I labored it. And I'm going to tell you, that's all this thing had. Another phenomenon or a question a lot of people have, they say when the compression part of this right here is not symmetrical, there's a valve issue. It's not symmetrical here because it's under load. Look at how crooked that is. It's way along on the trailing edge on the power side compared to the leading edge. And I find that quite a bit. And then when you go back to when there's no load on it, it's all happy and pretty again. So I never do take a whole lot of faith in saying the compression stroke, the peak is crooked or it's leaning like the leaning tower of Pisa or anything like that. That never has much value to me. Also, the shape of the section right before the exhaust valve opens right at the very bottom of the power stroke. Some people say if it's not shaped like a saucer, you have a valve issue that they're not in time. And I've seen lots of them where they come down like this sharp. Some of them they're nice and lazy down here, and then they go up sharp, and at different RPMs that changes drastically. And I've never ever been able to correlate that to valves being out of time or anything like that. So I'm not done playing yet. Still have some more stuff to do. So I thought I'd do one right from the start. Yeah, there we are. That's how I set it up. I used 2 pressure transducers this time. And just to show you, I started everything at 0. Here's at 0 and here's at 0. And here's where I started it. First turn, higher compression, no vacuum, makes a little bit of vacuum, compression goes down. Right here is when it started. So this is when it kicked faster. That's why this one's a little higher, because this is after the first ignition event. So it spun faster. And the blue trace is in the intake manifold. That's a capture of how much pressure is in the intake manifold. Started with nothing. After it started, we got about 20 inches of vacuum here. When it sped up right after it started, and then it leveled off. Right here, I snapped the gas pedal. So you can see a direct correlation between the intake pressure right here. When I lose vacuum in the intake, it causes the compression to rise every time. The more I lose, the higher the compression. And as a side note, if you had hooked up to secondary at the same time, because compression inside a combustion chamber is actually resistance, if you put a secondary capture, it would also mirror the compression and the vacuum. It would be idling along here nice, and when you snap it, the peak of the secondary would rise along with the compression and along with the pressure in the intake manifold. And I know everybody knows that, but I thought I'd throw it in just for the hell of it. Mac would be proud that I brought up secondary in this. So there's your dead proof that that's how come when you snap the throttle, up goes the compression, and it doesn't have anything to do with valve overlap. Doesn't have anything to do with whether you were good and Santa Claus was going to bring you a present, or did the Easter Bunny forget your Easter eggs. It's just a simple matter of how much pressure is in the intake manifold, because that affects how much stuff is in the cylinder for the piston to squish, to put it in plain language. Now, if that's not enough, I did another capture without moving the throttle. Had it hooked up the same way. I got one pressure transducer hooked up to the spark plug hole. I got another one stuck in the vacuum part where the PCV valve would go. And I got the brake booster line off, which is on a different end of the manifold. And right in these sections here, I bled the air off of, or the pressure off the brake booster line, so that it affected the pressure in the intake manifold and it lost its vacuum. And every time I did that, up goes the compression. Absolutely the same as if I stepped on the gas pedal. The pressure in the intake manifold changes, less vacuum, more stuff in the cylinder, higher compression. Really simple. So what about higher RPM makes higher cylinder pressure? We kind of did this one already, but we might as well do it again. Here's the engine running, idling right here. 700, 800 RPM, whatever it is. I don't really remember. Stepped on the gas here, and I held it. 2500 RPM. As everybody can see, higher RPM actually does not raise cylinder pressure. The throttle being depressed raises it momentarily. But when the engine starts to level out and it gets real happy with the RPM and it creates more vacuum in the intake system, or more vacuum in the intake system, the compression actually goes down a whole bunch. This thing has, at 2500 RPM, only 30 pounds pressure in the cylinders, and it had almost 60 idling at 600 or 700 RPM. And it's for real. I wouldn't kid you. There it is. Like, there's no tricks. So that's what I found out. That's what I tried to dig up from my old captures, and there was always bits and pieces missing. So I went the other night, I stayed after work, and I made these. I thought it was easier to explain my theory as to why the pressure transducer gives us the results it does when we step on the gas, or when we put it in gear, or when the exhaust is plugged. And apparently, so I'm told by Mr. CRB, that this is not going to be good enough, because he put captures up and his captures don't seem to make any sense. This is his bad capture. We're going to call it 90 pounds compression with 20 inches of, or 20 pounds pressure in the exhaust. Now we just proved that exhaust back pressure causes the compression to go higher, right? That was with a car with one catalytic converter, one plugged exhaust. This vehicle of Rich's has two converters, so half of the engine can be plugged, which he showed us. The other side of the engine is not plugged. The side that's not plugged actually does have higher compression. So how the hell does that happen when we just proved plugged exhaust causes compression to go up? And he went and made it all pretty for us. He put them in the same capture. Well, I have a theory for that one as well. His bad capture, which is this one, has plugged exhaust, and hard to tell with this thing he calls a scope that he made these captures with, because I can't tell by this big fat line and I can't put a cursor on it, but you can see the zero line, you can see the intake, how far below the zero line it is, and we know when intake pressure goes up, so does the compression. If you look in this capture, you cannot see the zero line. The intake pressure is higher on the side that is good, therefore the compression is also higher. So my theory is, without knowing exactly which cylinders he's hooked to, when this exhaust pressure was expelled back into the intake system from the bad cylinder, for the cylinder with the plugged exhaust, this guy over here, his intake valve opened up, so this exhaust raised the pressure on this intake and drove his compression up. So the one bank with the plugged exhaust is actually, every time the intake valve opens on a cylinder with plugged exhaust, it's pushing that pressure into the intake manifold and driving the compression on the companion cylinder higher. And I'm assuming that Rich picked a pair of cylinders that are really easy to get to at the front of this engine, so he got himself some companion cylinders, and the plugged exhaust is driving the compression up on the side where the exhaust is good. And that is my theory as to why his captures don't really make any sense. And that's all, folks. Have a nice night, and if you disagree with anything I said, you just let me know, because I got thick skin